Here, I am introducing another example of statically indeterminate problem. This problem asks you to calculate the stress generated in the two sections and displacement of the joint of the two materials. At first glance, this problem may look like a problem of bars connected in series. However, the concept is much the same as the previous problem of bars in parallel. The key in this problem is both ends are fixed and the force is applied at the joint part. This is a typical statically indeterminate problem. The key of this problem is the Young's modulus of the left part is different from that of right part. There is a similar problem where the diameter of the left section is different from the diameter of the right section. Anyway, in this problem, we are connecting the bars of the different Young's modulus and applying a load toward the right direction at the joint part. Now, we are solving this problem. We know the value of external load P, but we do not know the actual forces at the left and right. So, we start by provisionally defining them as P1 and P2 respectively. After then, we derive the stress and strain from each load. This calculation process is similar to the process introduced before. We get the stress as the loads divided by the cross-section area. We get the strain at each section as the stress divided by the Young's modulus. By using the values of the strains, the elongation can be calculated. Although you may think that the solution to this problem is just the sum of these elongations of the left and right section, you should notice that P1 and P2 are still unknown. So, the answer is wrong if you just add these two values together. We need to apply the condition. The total elongation of the bar is calculated by adding two values together, and the total elongation is 0. So, we get the relationship. Then, we get the equation by substituting the results of previous calculation. Another equation is derived from the relationship among P1, P2, and the external force. You may notice that the difference between P1 and P2 is P, as the following equation. We are focusing on this relationship in the solution of this problem. It may be easier to understand by just focusing on the bar of the left side. Assuming that the bar of the right side does not exist, then we can forget about P2, and only P1 acts on the bar of the left side. In this case, P equal P1. Assuming that the bar of the left side does not exist, the load P2 acting on the bar of the right side is minus P. In this case, P equals to minus P2. Since both loads are connected, the result is this equation, P equal P1 minus P2. There is another way to think about this. You may consider the case of no external force P. If the left side of the above equation is 0, then we get P1 minus P2 equal 0. This means that P1 and P2 are equal. In this case, the problem becomes just pulling an ordinary bar from both sides. The axial force is P, no matter where it is cut. We can also observe this way of thinking in the given relationship. Anyway, it may be useful to remember that the load acting at the connected part is the difference between the axial forces acting on the left and right bars. Let's come back to the problem. Now, we have two equations associating P1 and P2. Then, by solving the equations simultaneously, we can derive the solution to this problem. We are solving the two equations. One is the equation which was already introduced. That describes the total elongation of the bar is 0, and the other is P1 minus P2 equal P as simultaneous equations. Then, we obtain the loads P1 and P2 as these equations. Once we have the loads, we already know what to do next. The stresses on the left and right can be calculated by dividing these loads by the cross-section area. We notice that the stress generated in the right bar is negative. Since the joint part is compressed against the right side is in compression and the stress is negative. The next step is calculating the displacement of the bar. The positive and negative should be carefully considered in the calculation. The positive and negative signs of displacements of the left and right parts of the bar correspond to the stresses. The elongation on the left side is given by this equation. It may be called a symmetric polynomial in mathematics. In this equation, you can swap L1 and L2, E1 and E2. You may find that this answer is reasonable by checking these factors.